Dear children, in our everyday life, we rarely come across pure substances. Normally we use mixtures. For example, tea, milk, or a gold we are wearing, the gold jewelry we are wearing, it is a mixture of copper and gold. Or we can say the medicines, the cough syrups, or oxygen dissolved in the water. Today we will deal with the solutions, particularly liquid solutions, and it is your Unit 2 of Class 12th. First of all, what is a solution? A solution is a homogeneous mixture of two or more components. In your syllabus, we will deal with the binary solutions. Binary solutions means two components. One component which is in excess is known as solvent. The other component which is present in the lesser amount is known as solute. For example, in a sugar solution, sugar is solute and water is a solvent. A solution has two components, the solute and the solvent. The solvent is the substance in greater amount and the solute is the substance in lesser amount. Now, in our routine language, we say a solution is dilute or a solution is concentrated. That is, a dilute solution which has a lesser amount of the solute. In a concentrated solution, the solute is in larger amount. But when we do the experiments in the lab, we can't use this dilute or concentrated. We have to express the composition of the solution. Now let's see how we express the composition of the solution. There are different ways. Let's discuss them one by one. Mass percentage. Mass percentage is the mass of the solute divided by the total mass into 100. For example, if I say 10% glucose solution by mass, it means 10 grams of glucose and 90 grams of water. So if I want to calculate the mass percentage of glucose, then 10 divided by 100, that is the total mass, 10 grams of glucose plus 90 grams of water into 100. The other way of expressing concentration is volume percentage. The volume of the component divided by the total volume into 100. It is not different from mass percentage. In the mass percentage, we take the mass, that is in the grams. In the volume percentage, we measure the volume, that is in the liters or milliliters. The third way is the mass per volume percentage. It is the unit normally used in the pharmacy. Mass by volume percentage. Mass of the solute in grams divided by total volume of the solution into 100. Parts per million. We use this way of expressing the concentration when our solute is present in very minute quantities. For example, when the waterworks supply water, to prevent tooth decay, they add the fluoride ions. The fluoride ions are added in parts per million, that is in the traces. Let's see what's this. It is the number of the parts of the component divided by the total number of parts of all the components into 10 raised to power 6. Mole fraction. Mole fraction is defined as the number of the moles of the component divided by total number of the moles of the components into 100. Here you can see n, that is small n divided by small n plus capital N, where small n is the number of the moles of the solute and the capital N is the number of the moles of the solvent. Molality. Molality is defined as the number of the moles of the solute per kg of solvent. Here, molality is independent of temperature because molality depends upon the mass of the solvent, and mass is independent of temperature, therefore molality is also independent of temperature. Molarity. Molarity is defined as the number of the moles of the solute in 1 liter of solution. Molarity is temperature dependent. Why temperature dependent? Because when the temperature increases, the volume also increases. And when the volume increases, the molarity decreases because the molarity is depending upon the volume. So dear children, we have just now discussed how we can express the composition of a solution. We can use any one of them. Now, let me deal with the solubility. What is this solubility? Solubility is defined as the amount of the substance dissolved in the given amount of the solvent at a given temperature. The solubility of a gas in liquid was quantitatively described by Henry's law. Henry's law states that the solubility of a gas in the liquid is directly proportional to the pressure of the gas. That means higher is the pressure, greater is the solubility of the gas in a liquid. Mathematically, Henry's law is pressure is equals to Kh into mole fraction, where P is pressure, Kh is Henry's law constant. From this relation, we can very well say that pressure is directly proportional to the mole fraction of the gas. Let me take an example. We drink cold drinks, the soft drinks. We find them tasty when the fizziness is there, when it is sealed under high pressure. Why these cold drinks are sealed under high pressure? It is just to increase the carbon dioxide in the concentrate of the cold drink. When we open the cold drink, after some time we don't find it tasty. Why? Because the pressure is lowered and the CO2 which is dissolved in the concentrate is released. So, we can say that the pressure of the gas is directly proportional to the mole fraction of the gas. Now, the solubility of the gas is inversely proportional to the temperature. Now, let's see why this is so. When we dissolve a gas in a liquid, the process is exothermic. Exothermic means the heat is released. Now, when we increase the temperature, it does not favor the solubility of a gas in a liquid. Let me take an example. The aquatic life is not comfortable in the summers because during summer the temperature is high, and when the temperature is high, the solubility of oxygen in water is low. But this marine life, this aquatic life is very comfortable in winters. In the winters, the temperature is low, so the solubility of oxygen in water is high. I think that it is all very much clear to you. Now, let's switch over to the solubility of a gas in a liquid is inversely proportional to Henry's law constant, that is Kh. Higher is the value of Kh, lower will be the solubility of a gas in a liquid. Also note that different gases have different Kh values at the same temperature. The value of Henry's law constant is a function of the nature of the gas. Now let's discuss the vapor pressure, the lowering in the vapor pressure and the Raoult's law. First of all, you must know that there are two types of liquids, volatile and non-volatile. The volatile liquids, those who evaporate, and the non-volatile liquids do not evaporate. That is, they do not change into vapors. Now let me tell you vapor pressure. For example, I have this pure solvent and it is volatile and it is taken in an evacuated vessel and partially filled. Since it is volatile, it will change into vapors, and now you can see these vapors. These vapors will exert pressure on the surface of the liquid. The pressure exerted by these vapors on the surface of the liquid at equilibrium is known as vapor pressure. The vapor pressure is dependent on temperature only. In a solution, the vapor pressure of the solution is lower than that of the pure solvent at the same temperature. The vapor pressure of the solution is lower. Now how it is so? This is the pure solvent. Now I am changing it into a solution. I have mixed a solute into it. The solute molecules will go into the bulk and they will come on the surface also. Now, when these solute molecules come on the surface, the fraction of the solvent particles on the surface will decrease. These solute particles are non-volatile. They will not change into vapor. Only the solvent molecules will change into vapor. But since the fraction of the solvent on the surface is decreased, now we can see that there are less vapors at the same temperature. This we can say that there is a lowering of the vapor pressure when a solute is mixed in the volatile solvent. Let me discuss now the Raoult's law. Raoult's law states that for a binary solution of the two volatile liquids, say 1 and 2, both the components would evaporate and equilibrium would establish between vapor phase and the liquid phase, and the total pressure would be equals to the sum of the partial vapor pressures, that is P1 and P2. For such a situation, Raoult's law states that for a solution of the volatile liquids, the partial vapor pressure of each component in the solution is directly proportional to its mole fraction. Mathematically, the Raoult's law is the pressure of the solution is equals to P01 x1 plus P02 x2, where P01 and P02 are the vapor pressure of the pure component 1 and 2, and x1 and x2 are the mole fraction of the component 1 and 2. Vapor pressure of the solutions of the solids in liquid. For example, if we prepare a solution mixing sodium chloride or glucose or urea in water, then this sodium chloride or urea or glucose are non-volatile. In such a situation, the Raoult's law states that the vapor pressure of the solution is directly proportional to the mole fraction of the volatile component, that is, the vapor pressure of the solvent. The decrease in the vapor pressure of the solvent depends on the quantity of the non-volatile solute present in the solution. Only solvent molecules are present in the vapor phase and contribute to the vapor pressure when the solute is non-volatile. So dear children, just now we have discussed the ways of expressing the concentration, Henry's law, that is governing the solubility of a gas in a liquid, how the solubility of the gas is pressure dependent, temperature dependent, and Henry's law constant dependent. And then we studied about the vapor pressure. The lowering of the vapor pressure